one or two other limits at the very back of last Friday's sheet that we didn't quite get to. So we did the 1 plus x to the 1 over x thing, and kind of talked about how that's basically a compound interest formula. What was the one that was after that that we didn't get to? As x goes to 0. Okay. And similarly, we'll have to take this one on faith for right now. And we can sort of justify it a little bit better later and also interpret why it is what it is. So just kind of keep that one in mind, that it's for a little bit later. So there's two exercises on there. So I wanted to look at the first one at least, and just give you guys a sense for how you use these. So I think it was something like sine of 4x over x. Is that right? Okay. So this looks a whole lot like sine of x over x, right? But it's not exactly that. And so we're kind of boned. But what tricks do we have up our sleeve in terms of dealing with limits that we don't know? Conjugate, it being obvious and being able to plug in, or multiplying by some, well, I guess the conjugate kind of comes in this, multiplying by something that basically is 1 but doesn't look like 1. Okay. Can we plug in here? No, because if we did, what would happen? Yeah, we'd get 0 in the denominator and actually also 0 in the numerator, right? Because sine of 0 is 0. Okay, so we can't do that. There's obviously no square root stuff, so there's no conjugate trick to use. And so the only thing left that we could possibly try is multiplying by a disguised form of 1. Okay. Any ideas as to that disguised form of 1? Well, yeah, not so obvious, is it? Well, let's try this. Okay, you'll see why I'd pick that in a moment. Okay, so let's multiply it out. And so I'm going to write this as 4 sine of 4x over 4x. Okay, same thing, I've just kind of, arranged it slightly different. Now, as x goes to 0, what does 4x do? Well, okay, so as x goes to 0, 4x also goes to 0, right? So this is the same as the limit as 4x goes to 0 of 4 times sine of 4x over 4x. Yes? Okay, now, what I want you to realize is, so let me, up here in green, write the other limit, the one that we were sort of starting with. And you notice how in the new limit, 4x is playing the role that x did in the one that we just took on faith, right? So 4x, x, smiley face, are they really any different? No. And so I can think of this as being sort of the same as limit as smiley face goes to 0 of 4 sine of smiley face x, or I guess just smiley face, sorry, over smiley face. Okay, well, what's the limit of the smiley face part based on what we had from before? Or sorry, this thing, which was what? 1. Okay, so if that part is 1, what do you think the whole thing's going to be in this case? So let me rewrite it slightly. So what's the thing in the inside of the parentheses? That's the one we just had to take on faith. It's 1, right? Okay, and then it's times 4. So what do we get? 4. Okay, so does that kind of make sense? This is sort of the game you have to play. And then the other one is sort of similar, so maybe give that one a shot on your own and see what you come up with. Okay. Yeah. Now, it does beg the question: why is this true in the first place? We could graph it, and that gives us some pretty good kind of evidence that one makes sense. Okay. Um, there are actually geometric ways that you could prove it. So, like, go back to high school geometry, and if you draw the right diagram and kind of think about it in the correct way, then actually you can show that this does make sense. Yeah. Because of the 4 that was right there. So I multiplied by 4 over 4 because of that 4. I wanted the bottom to have a 4x to match the 4x that was on the inside of the sign. Okay. And since 4 was already there, that's why I picked 4 and not any other number. Okay. Um, and then, so I wanted to have a 4x in the bottom. So I put a 4 there. But of course, I can't like not do the same thing to the numerator because otherwise I'm changing the quantity, right? So, as thou doest unto thy denominator, thou shalt doest unto thy numerator. Huh? Yes, exactly. Euclid 3:16. So, actually, interestingly enough, um, you guys know, maybe it's been a while, but Stone Cold Steve Austin, right, the wrestler, Austin 3:16. Well, of course, he was riffing off of John 3:16, right, which says what? Right. So guess what Euclid Book 3, Proposition 16 basically says? Uh, for Euclid did so love the circle that at any point on it he gave its only tangent. So that's not exactly how it's worded, obviously, but given a circle and a point on the circle to construct the tangent line through that point, and there's only one of them, right? So, yeah, it's better in Greek, as is always the case with these things, but yeah. Okay. Anyway, so right. So I didn't just pick 4 out of thin air here. I picked it because I knew it was going to sort of solve the problem. And as you guys kind of work a few more of these, I think you'll start to kind of see um, uh, the range of tricks that you're going to throw at these things is not something that like you can't just memorize all the tricks, right? There's just too, I mean, there's essentially infinitely many of them. And so what you have to try starts to come with experience and looking at examples that like, that looks a lot like this other problem I remember doing. Let me try and adapt what I did over there. And eventually you start to get kind of an intuition. And eventually you get to the point where you can just look at these things and instantly know what they are. Um, that tends to happen after you get a PhD, but yeah. Anyway, okay. So let's get to today's stuff, which is all about infinity. So let's take an example rational function here, and I'll graph it in a second. But before we do that, let's just um, think about what's going to happen when we do graph it. Okay, and so we got this function, and what, of course, the point of the day is to think about what about the limits of this thing. Um, so if I were to graph this thing, what am I going to see? And there's going to be curvy stuff going on, right? But in particular, there are 2 very important lines that I need to draw. What are they? Actually, 3 of them, but hmm yeah, asymptotes at x equals 3 and x equals -4, right? Vertical asymptotes. Okay, and then I also know that there'll be a horizontal asymptote at y equals 0. And how do I know that, by the way? That there should be a horizontal asymptote also. What's the degree on top? What's the degree on the bottom? Huh? 2, because it's got 2 linear factors, right? Um, and so the degree on the bottom is bigger. And so if I go out to infinity or minus infinity, I know I'm going to go to 0. We'll actually prove that in a minute. Okay. Um, But, right, so if I graph this, I'm going to have one horizontal asymptote and two vertical asymptotes. Do I have any holes or anything else, any other sort of special things going on? Why not? How do we know that we don't? Well, look at the numbers here, or the linear terms. Does anything cancel? And it's when things canceled that we started to see things like holes. We don't have any cancellation going on here, so there's not going to be any holes. It'll just be asymptotes instead. Well, okay. So what really, I guess, is an asymptote? Like, what does that even mean? Right? So if I draw, just a vertical line like this, an asymptote, like it's going to be like this sort of thing, right? So what does the word asymptote mean? Yeah, you never actually get there. So geometrically, they get, basically pick a distance. I can find a place where they get closer than that distance, but they never actually intersect. Okay. Um, and actually, the word asymptote, um, and if any of you ever say asymptote, okay, I'm going to beat you with the stick that's sitting over there by the door. Okay. Um, this comes from Greek, asymptote. Uh, Pipto means to fall, or um, pipto, then in mathematics, tends to mean to intersect, to fall on each other. And pipto means to not do that. So they are not falling on each other things. Right? So hashtag liberal arts college. Anyway, um, so yeah. And so what does it mean then for something to approach a vertical asymptote? Well, how could a curve get closer and closer to this vertical straight line without ever actually getting there? What does it got to do? It's got to basically start to become almost parallel to that line, right? Which means it's got to go essentially start to curve upwards or downwards, one of the two, okay? Which means in terms of the y values, where are we going with this? Yeah, to infinity or perhaps to minus infinity in the other direction, right? And so this would be a situation where we would expect that the limits are actually infinite or negative infinite. Okay, so does that kind of make sense? Okay, now, I do want to be clear about one thing. Does infinity exist as a number? No. Okay, so when we talk about a limit being infinity, strictly speaking, we're still within the does not exist category. But in some cases, we can be a little bit more explicit as to why it doesn't exist. Okay, and so if, like, strictly speaking, if I asked what is the limit as x goes to, say, 3 of this function, DNE is technically correct. No, you'll get a stick beating for that. Okay. Um, well, actually, it is DNE here and not plus infinity. And okay, we'll see why this is the case in just a second. Okay. So anyway, the point that I'm trying to make is that if we can be more specific and say plus or minus infinity in a given situation, do so. Okay. Okay, good. So let's go over to Desmos and let's graph this thing. All right, so what was it? X plus 2. And then I need some parentheses. And we need to divide. And what was it? X minus 3 times X plus 4. Yeah. Okay, so let's zoom out and kind of take a peek here. Let me change the color so it's more obvious. How about red? Because this is Wabash. Okay, so do we see vertical asymptotes where we would expect them? Yes. Okay. Do we also see that horizontal asymptote while we're on the subject? Yeah. Okay. Good. All right, so we see our vertical asymptotes where we'd expect them to be and the horizontal asymptote. And you guys remember talking about asymptotes and stuff in high school, hopefully, right? So that's not like, maybe it's been a little while, but we're Gucci. Yeah, okay. So, so let's take the situation that's going on over at 3. Okay, why would it be correct to say that the limit as x goes to 3 of this function does not exist? Yeah, there's an asymptote. Okay, but why can't we say plus or minus infinity in that case? Exactly. Okay, what's the right-hand limit? So limit as x goes to 3 from the right of this function. That one's plus infinity. What about from the left? Minus infinity. And so what is the limit? That one just flat out does not exist because infinity and minus infinity are not the same thing. Okay, so that the rule about one-sided limits still is in effect, that the left-hand and the right-hand limit could be different, and in this particular case, they are. Okay, so does that distinction make sense? Yeah? All right, now, similarly, what's going on over there at -4? Basically the same thing. The right-hand limit's infinity, the left-hand limit's minus infinity, the limit doesn't exist. Okay, so now, is this always going to happen where it's different on one side of the asymptote versus the other? I mean, it did with this function, but is that always going to happen? No. Can we come up with an example where it doesn't happen? Or where it goes either both up or both down? We can. Any brilliant ideas? I'll just use a real quick cheap one. How about this guy? Let me turn off the other one. How about 1 over x squared? That works, right? And so what's this one do? Both of them are positive infinity. So what is the limit? Also positive infinity. Okay. And it could also have been minus if I, flip the graph over or whatever. But yeah. Okay. So does that kind of make sense? Right. So like before, I'll often have to think, well, what's the left-hand limit? What's the right-hand limit? And go from there. Good? Oui ou non? Okay. Now, so that was basically talking about horizontal asymptote department. Okay. And in the case of the examples that we worked here, these first 3, right, this function was deliberately constructed so that nothing canceled nicely. Okay. If things did cancel nicely, what essentially happens graphically is that asymptote collapses into a hole. Okay. And then the limit might actually work out to be a specific number. Okay. And the cancellation sort of stuff we looked at last time. Okay. Okay. Good. Yes. Okay. Good question. So let me go back to the white sheet here. Okay, so how would I do this without a graph? Well, what I would have to do is first say, is there any magic cancellation that happens? No. Okay. And so what I'm going to have to think is, all right, if x approaches, so let me just do limit as x goes to 3 from the right of x plus 2 over x minus 3, x plus 4. Okay, because there's no cancellation that happened, and if I just plug in 3, I get a division by 0, that should clue me in that I'm going to be in a plus or minus infinity kind of possible situation. Okay, now, how do I know between plus versus minus without the graph? Right, with the graph, it was obvious, right? Was it going up or was it going down? Well, without the graph, what I want to kind of do is say, well, let me think of a number that's just slightly bigger than 3. Okay, 3.1 sounds good, right? And then look at each term and determine, is it positive or negative? Okay, and in this case, if x is bigger than 3, all 3 of those terms are positive, right? The numerator and the 2 factors in the denominator. Yes? So what happens when you multiply and divide a bunch of positive stuff? You get positive quantities. And that's how I know it's going to be positive infinity instead of minus infinity, because it's already positive, right? If it were going to go to minus infinity, I would need to start seeing negative numbers here at some point, but I don't. Okay, does that make sense? Okay, now, so this one is, as we said, plus infinity. Oh, that's the worst. Okay, whereas what about the limit from the left? Why is this one minus infinity? Yeah, exactly. So if we think of, well, what's a number that's slightly to the left of 3? 2.9, okay. X plus 2, is that positive? Yep. X plus 4, is that positive? Yep. X minus 3, positive or negative? Okay, so I've got a negative times a positive in the bottom. That makes the bottom negative. And I got a positive over a negative. That makes the whole thing negative, right? And so that's kind of the analysis that we need to do to suss out which way it's going to be. And then maybe this makes sense then why the x or 1 over x squared example that I put up on Desmos, why they both go up. Well, because what happens when you square something? It's always positive, right? So you don't have to worry about that sign issue. So basically, just use your noodle is the best way to do it. So, okay, good. Okay, so that was the vertical situation. Let's talk the horizontal situation. Because this actually gets, believe it or not, slightly more complicated. Okay, so let me go on to a clean sheet here. And so there's a key fundamental fact that we need. Okay, so two things are about to change. Well, actually, I guess one thing, right? Instead of letting x go to a specific number, we're going to let x go all the way off to infinity or perhaps minus infinity. Okay, in terms of the graph, what are we essentially asking? Where is the function going kind of long-term behavior? Like way the hell out there kind of thing, okay? And our key fact that's going to basically make all of this work is this property. If I have a term 1 over x to the n, and the n is positive, that means that I don't have like a negative exponent that I have to flip up into the numerator, right? So as long as I've got sort of a genuine fraction with these things, what happens when you start dividing by larger and larger and larger quantities? You get smaller and smaller and smaller quantities. So what should we expect? The limit of this process would be 0, okay? Right, if I divide 1 by 10 trillion, I mean, are we basically talking 0 at that point, right? I mean, yeah, it's not technically 0, but it's so dang close that, who cares, okay? Right, and so basically everything we're going to do with these, with rational functions, which is to say polynomials divided by other polynomials, is going to come down to this fact along with the limit laws that we've already used, okay? So let's take a look at, actually, let's look at the example we just did instead of the one that's on the sheet here, just for fun's sake. So I want to ask, what is the limit as x goes to infinity of x plus 2 over x minus 3 times x plus 4? Okay. Now, for sake of demonstration, I don't have to do this, but it might make things a little easier to see. Can I go ahead and FOIL out everything in the denominator? Is that all right? Okay. What does it FOIL out to? Okay. X squared plus x minus 12. No. Okay. Good. So there's a trick that I need to pull. Okay. What I need to do right? We've already established there's no factoring, nothing cancels, right? There's basically nothing I can throw at this. There's no square roots, so conjugate kind of trick ain't going to work. What's the only other trick that we have up our sleeve? Multiplying by some funky, squirrely form of 1. Okay, now, in this case, it's not yet as obvious as to which funky form of 1 that we want to use. Okay, here's the one we're going to use. What is the largest power of x that you see in the denominator? Okay, x squared, right? So I'm going to multiply and divide by 1 over x squared. Okay, we'll see why this works in a minute, but always the biggest power in the denominator, even if the denominator doesn't have the biggest power overall. Okay, so in this particular example, the biggest power happened to be the denominator versus the numerator. Okay, not always is that going to be the case. We'll look at some examples where it's not, but always the biggest power in the denominator. Okay, yeah. Okay, so let's just take this on faith that that's a good move. And now what? Can we like multiply things out, maybe try and simplify, that sort of thing? Yeah? All right, so let's do it. So on top, what do I get? What's x over x squared? 1 over x, right? What's 2 over x squared? Well, I don't know, 2 over x squared. Okay, so you see how I'm distributing it to every term in the numerator? Yeah? And then simplifying as I go. Well, what about the denominator? What's going to happen there? What's x squared divided by x squared? 1. What's x over x squared? 1 over x. And what's minus 12 over x squared? Well, I don't know, minus 12 over x squared. Okay, so I distributed in the numerator and the denominator, and like I said, simplified each term as I went. Okay, so question Prägungsfragen on that process. Now, wake up, Robert. Hey, don't you get smarmy. At least he's actually made it to class a few days. Yeah. Okay, so now that we've done that, okay, first off, are we cool that I haven't done anything wrong here? Okay, so just distributed everything. And now what I want to do is two things. I need to use my fundamental fact, okay? And we're kind of pretty close to that. The other thing I need to use, though, is what is the limit of a fraction? Can I take the limit on top and divide it by the limit on the bottom? Provided that both of those exist, okay, which we'll make sure that they do in a moment. And then if I take the limit at the top, I've got the limit of a sum. Well, what's the limit of a sum? The sum of the limits, right? And same thing in the bottom, right? So I can then, using our limit laws, say that this is equal to, oops, got a straight line down there, would be equal to oops. Okay, so there I just applied two of our limit laws. Limit of a fraction is the fraction of the limits, and limit of sums and differences is sums and differences of the limits, right? Okay, now it may seem a little bit pedantic that I went down to that level of detail, but we kind of have to, so, because I said so, damn it. No. All right, so scribble that down. Oh, yeah, thank you. Although it'll end up not mattering. Okay, so why did I go down to that level of detail and put the limit on every little single term there? I mean, other than I'm a hard ass, or because we have to. All right, what was the reason for that? Well, look at our key fact. I've broken the problem down into basically a bunch of instances of the key fact, right? So what are all of those limits, or 4 out of the 5 of them, what are they going to be? Okay, by the key fact. What's the 5th one? Okay, so what's the one that's not one of the key facts there? The very first one right here. Okay, do we need to be brilliant mathematicians to know what that limit is going to be? Because it's a constant, right? Limit of a constant is itself. Okay, so what do I get here? I get 0 plus 0 over 1 plus 0 plus 0, and that equals what? 0. Okay? And so I know that this is what it meant to be a horizontal asymptote, is that this limit is 0, right? Graphically, what did it mean to be a horizontal asymptote? The values got closer and closer to 0 as you went off further and further along the x-axis, right? This is that like calculus way of explaining that. Okay, and would this work any differently at minus infinity than at versus infinity? In this case, nope, not at all. Right, so no worries there. Okay, now, any questions on this example before we kind of go on? Okay, and you guys might kind of be seeing where this might go, because there's a trick that we can play. Okay, so let's look at then the the example that's at the bottom of page 1 here on the sheet, right? Look that one over. Is that sort of the same thing here, or similar idea? Okay. In this case, what's our power that we multiply and divide by? 1 over, okay. Where did we pick the x squared from? The denominator. It just so happened in this case that the numerator's largest power was also x squared. That was coincidence. Okay, always use the one from the denominator. Okay, now what does it come out in this case? Comes out to 1/2. Okay, so things cancel a little bit differently, but sort of similar idea to before, and we get 1/2. Now, looking back at the original function, does that seem like we should have known this in advance? Why? Yeah, the ratio of the leading coefficients. Okay, so how many of you guys remember this trick from high school where all you have to do is, if it's top heavy, what's the answer going to be? Plus or minus infinity. Okay, if it's bottom heavy, what's it going to be? And if it's equally heavy, it's going to be the ratio of the leading coefficients. Okay, so in this particular case, that ratio is 1/2. But why is it true? Because of this limit argument. Okay, so is it enough to just say, oh, well, it's going to be 1/2 because that's the ratio of the leading coefficients? Is that good enough? No, of course not. Okay. What is good enough would be this kind of limit argument where you're breaking it down into little pieces. Okay. Now, that said, isn't it kind of nice to know what the answer is before you get started with the problem? Yeah. So using the high school trick as sort of like a cheat, a quick check, by all means, right? I mean, it's true. Okay. But this limit process is why it's true. And that's what we care about in college math, is not just what the answer is, but why it is. You must have a little sister. Oh, okay. Well, that works too. Yeah. Uh, um, okay. So, does that make sense? What about if the numerator is bigger? It's going to be plus or minus infinity. And the reason that'll happen is because if the numerator's got a bigger power, after you do this cancellation, you're going to get at least an x term, maybe x squared, maybe x cubed, and so on. Well, what are all of those going to do as x goes to infinity? They're going to be infinity or perhaps minus infinity. How would you know? Basically, based what their coefficient is. If the coefficient is negative, it'll be negative. If it's positive, it'll be positive. Okay, make sense? Yeah. Okay. So, for sake of practice, um, why don't you guys let's look over to the next page and all right, A, you two do B, C, A, B, you two do C, you and Arthur do A, and you guys do B. And furthermore, wouldn't it be great if there was lots of blackboard space all over the classroom that you guys could write on? Yeah. Okay. So at least one A, one B, and one C, please hit the boards. Yeah, this is the get to work part of calculus. Wake up, Robert. What time did you go to bed, Robert? 1. Why did you go to bed at 1? Sorry. No, just do the limits as written. Yeah. So only horizontal in this case.